quantum is such an important technology, and I've been in the space for a couple of years now. And when I look back at sort of the last century, the amount of progress that we've made in our country has been absolutely phenomenal. You think about the beginning of the last century, and we were entering into an era of having electricity in automobiles and manufacturing, and then we went to the moon. So these are so many incredible things, and I'm so looking forward to what we're going to see in this century. And I do truly feel like quantum will have the greatest impact on that. So we're living through history right now, and we're setting the course for the future. And all of you guys are part of that. And it's really exciting. The other thing that I really stress is having the notion that there is no second in quantum. So in the US, I think it's incredibly important, and we saw this earlier this week, that there's so much progress happening and so many amazing things happening in our country to progress quantum forward. So with that said, I think that I have the distinguished honor to introduce our next speaker and Nobel Prize-winning physicist. There you are, John Martinis. Thank you so much.
Yeah, thank you very much for the opportunity to speak today. As I was walking into the room today, I was passing the casino, and I was thinking, the real high rollers, the billionaire high rollers, are in this room today. And that's what we're trying to do, is create wealth. We understand there's a lot of things to do, a lot of things we have to build and demonstrate. But I'm really excited that there's so much potential in quantum computing. Can we have my first slide, please? Oh, I'm supposed to do it. Very good. Okay. I'm going to talk today a little bit about the history of superconducting qubits from my thesis experiment, where we was able to awarded the Nobel Prize for, and then talk about how it's developed and what we're trying to do in our company, Qolab. The thesis experiment really came about because we all understand that quantum mechanics is the physics of the small, how the atoms work, molecules, electrons, photons, etc. But at the time, there was a real question there, was whether you could see quantum mechanics in a macroscopic system, in particular, for a chip about a centimeter size operating at microwave frequencies that's involved with a macroscopic flow of millions and millions of electrons through this electronic device. And this was motivated by the kind of Schrödinger cat paradox. Maybe it's a way to explain the Schrödinger cat paradox. But in the end, it was just a nice experiment to show that you could see quantum mechanical behavior beyond what we normally expect quantum mechanics is good for. Now, in doing this experiment, it actually was very hard at the time because people, it's hard to believe right now, they didn't understand that this was a microwave experiment. And that's the first thing we did. We did some experiments, didn't work very well. But over a certain amount of time, we figured out that you had to do your microwave engineering. And I'm very proud of this particular design that we had here, which kind of exhibits the microwave behavior. It's something I machined myself, okay? You see on the diagram, you have a little chip on the right with a Josephson junction, a cross of two superconducting wires, separated by a weak link Josephson junction. And then that's connected to this cylindrical tube, which has a microwave, it has copper powder in it that is a filter that dissipates energy as it goes down, because we want to get rid of all the noise that's coming from high temperature and even at 3 or 4 Kelvin. And we have SMA connectors, they inject the microwaves and a bunch of filters and the like. But it's really the microwave filtering that was absolutely key in getting this to work. And I find it funny that 40 years later, we're still using that microwave filtering. And what we're doing at Qolab is trying to bring the next generation after 40 years to miniaturize and make that better. And also, other microwave components that we have to figure out how to do properly in this device. How did we see quantum mechanics? Well, what we do is we see how the superconducting system, if you put enough current into it, you then transition from the superconducting state to a normal state where there's a voltage across the device. And that transition occurs because you're escaping from a qubit potential that describes the energy of the Josephson junction and the like. Now, I don't have time to go into the details of this, but the big kind of smoking gun proof that you're seeing the quantum mechanics in the system is looking at energy levels. And for example, if you look at incandescent light, like coming out here, that's white light. You have light of all different frequencies. But kind of the smoking gun of quantum mechanics, which made it so mysterious over 100 years ago, was that when you excite atoms like neon gas, you put a discharge of neon gas, you see distinct colors that come out of that. And these distinct resonant frequency, microwave frequencies observed in these systems is what really shows that it's quantum mechanics. So what we did here is we had an experiment where we measure the escape rate out of a zero voltage state versus some current that we go through the device. As you change the current, you change the frequency of the qubit, and then we inject microwaves. And we find in this particular plot that there are these three peaks here that this corresponds to how the escape rate increases when we put on the microwaves. And this is when the microwaves are resonantly, energetically, coherently giving energy to the quantum system. And in that, these three peaks are actually telling you that you're seeing transitions from the zero state to the one state, ground state to the first excited state, 1 to 2 to 2 to 3. Classically, that's a big smear. Quantum mechanically, you see three distinct lines. And that is really the smoking gun evidence that we're seeing quantum mechanics in this system. And it was a real thrill for me sitting in the basement of Burj Har to see those three peaks, knowing that this is really showing quantum mechanics in this system. Now, of course, those quantum energy levels is how we're going to encode qubits. So that was a very important experiment at the time. So what I'd like to say is, building these systems, what we've seen over the last 40 years, is that this is a new way to make quantum systems. We're all used to quantum systems from the periodic table with electrons and photons and other things, but here we have building blocks of capacitors, inductors, transmission lines, junctions, where we can build these artificial atoms. And of course, what's particularly interesting is if you can build an electrical artificial atom, we can then use all the technology of semiconductor manufacturing, integrated circuits, to build more and more complex circuits and hopefully build a quantum computer. This is just an experiment I did at UC Santa Barbara in 2008, 2009, where we had a qubit, which is a little circuit on the left, coupled to a resonator, which stores information. And what was really interesting about this experiment is we were able to very carefully calibrate how that quantum system worked, how the qubit worked, how the coupling to the resonator. And just using the calibration and then just integrating the Schrödinger equation, we were able to build very, very complex quantum states. And on the right, I show some of the quantum states, 0 plus 5, 0 plus I3 plus 6, where on the top you see what you expect theoretically, on the bottom you get what you do experimentally, what we measure. Very good correspondence. And what I would say, this was a really landmark experiment for my particular experimental program, because it proved that if you just calibrate, make your qubits carefully, engineer it right, calibrate it right, you can then build these very complex states. And you can just trust quantum mechanics, trust you're integrating the Schrodinger equation, really showing that it's possible to generate complex quantum states. And at that point, I really had a feeling that, yeah, it might actually be possible to build a quantum computer given that this experiment worked so well. And these were not the best qubits at the time, but we could get that to work. So fast forward till I'm moving my project to Google and working on the quantum supremacy experiment. I like to ask the question as, does macroscopic quantum computation, which is going to be very, very powerful because it's a kind of a parallel computation, does it obey quantum mechanics? Does it work? Or is there more dirt effects that you see that makes it not to work? So this is the Sycamore processor, 53 qubits. You see the chip there. And with a Hilbert space 2 to the 53, you have a computational space that's very macroscopic, 10 to the 16. And the nice thing about the experiment is that it worked just as you expect. There were errors in it. Qubits weren't perfect, but there were really no additional errors that we saw that we didn't expect. So this was very good to show that the basic physics of the quantum computation work. Of course, over the years, people have made it bigger and better, and we're building on that. But I was really pleased to see that at the time. Okay, so it was really nice for me. 1985, there was my thesis experiment. 2019, the quantum supremacy experiment. Okay, what's next? What am I thinking about? What are we going to do in the future? So to motivate that with the last minutes here, I'm going to just really honestly about what's going on right now with superconducting qubits. They work great. They're really fast. You can calibrate them well. We understand how to build them. Here's the picture of what people are building right now. And you see just a bunch of wires and coax and microwave components down here, which is good for prototyping. But how are we going to go and make, let's say, a 1,000,000 qubit quantum computer? And what I'd like to say is what we're doing right now is great for prototyping initial quantum computers, but it kind of looks like computers in the 1950s or 1960s. You have a few transistors, and then you have tons of wires connecting everything together. And what we want to think about how we want to go in the future to build this. And the obvious answer is, well, we want to build like microprocessors in the 1970s. You integrate all the transistors and the wiring together to build a chip. So that's what we want to do, is figure out how to do that. And this is great for now, and people will do experiments like that. We want to build something like this. So this is how are we going to do that? Well, what we're doing in our company is we're working with Tool Builder, Applied Materials, and other semiconductor manufacturers to figure out how to build our qubits better. And we think that superconducting needs these semiconductor fabrication, 300 millimeter, need to use the most modern tools to perfect the interfaces and do everything right. So that's what we've been doing for several years now, and understand how to do that in a good way. But to be, that's very aspirational. Just to be very, very clear, is right now the qubits are made with liftoff, which is a technology, let's say, of the 60s or so. We need to use deposition and etch, so we're moving a process over to that. We were able to make qubits in that way. We're learning how to make them better. We feel very optimistic about that. We really like working with these advanced tools because we can make basically perfect interfaces and layers and the like. And then finally, we want to talk about wafer scale integration, which is really starting to focus now on how are we going to go and put together the system. And this is a slide of what we're trying to do. We want to do wafer scale integration. Here's a picture of a Cerebras AI processor that's made on kind of a single die, single chip on a 300 millimeter. And we want to use wafer scale integration like that and advanced semiconductor manufacturing to get to inexpensive scaling. So we eliminate all the wires. So here's kind of a diagram, simple diagram of what we're going to do. We're going to have a qubit wafer about this size, 20,000 qubits, that's then bump bonded to a wiring wafer that brings out some filters and wires, and you go from the 20 millikelvin low temperature to 303 Kelvin, on a silicon wafer. That's not so obvious how to do that, but we know how to do that. And then at 3 Kelvin, where we have some heat load possible, we have our cryo-electronics wafer, CMOS, digital, superconducting digital logic, and then we go with some flex wiring up to high temperature where we build a control system. So we're trying to integrate this all together and make it so that this is relatively inexpensive to build, because it's just making wafers, which you can do en masse, bump bonding them together, building these proper modules. There's a lot of innovation that goes into replacing all the components in these present systems to make it integrated, but we have a way to do that. And in fact, we actually say in this particular archive paper right here, how we're going to do that. And we also talk about how we're going to work with various partners here, which I've described here, on how to do that. Hewlett-Packard Enterprise is a supercomputer maker, so they're kind of at the high end. Western Digital, Applied Materials, other companies are in the low end, working with universities and startup companies and the like to make this happen. So we're working in the Quantum Scaling Alliance to put all this together and build a quantum computer properly. Of course, what we want to do is put this together, build a general purpose quantum computer. You've seen pictures of this here. We think that by building it this way, we can make a little bit more compact and cost-efficient quantum computer. But obviously, it's going to be a big system, but not outside the realm of what everyone is really thinking here. So with that, just let me summarize here. I think there's significant hardware manufacturing challenges in order to scale up existing superconducting qubits. They work great, they're fast, lots of ideas, lots of new ideas on architecture, really excited about that. We think we have to manufacture this in a better way, more reliable way, and bring the cost down. We're working on that. And to do that, we're leveraging the semiconductor expertise to fabricate this. So we have an active consortium to do that together. And our name, Qolab, is Q plus collaboration, so we naturally want to do that. And finally, I would say, what's not talked about too much is how much does it cost to build a quantum computer, okay? And if you were to take the present kind of technology people are working on, that's billions of dollars, tens of billions of dollars. We have to bring the price down, the cost down. And basically, we just want to leverage what the semiconductor industry has been doing for decades, leverage that technology, and we think we can put together a quantum system based on modern technology that works better, can be assembled better, much more cost effective. In the end, we need to make lots of data centers of quantum computers, and we think that can be also scaled. So with that, thank you very much for your attention. I might have a couple of minutes for questions. Yeah. Okay, thank you.
I think we had a question over there,
Yeah.
Where we are today, talk about what for us to get to that threshold.
Did you happen to...
It was, what you've done since the 1970s and what you've been able to accomplish to get there today.
For my company? Or...
And by the way, if you can, everyone log into the app and write in your questions if you can. But since we're in the midst of this, yeah, if you could just come up, maybe
come up because
yeah.
it's kind of, I have bad hearing too.
the 1970s,
Yeah.
where we are with the
Yeah.
microprocessor and the
Yeah,
computer
right.
machine. What needs to be true scientifically for quantum to get to the personal computer?
Okay. So how to get to kind of a personal computer era? I would love to make personal quantum computers. I think that's going to be hard. If you look at what's happening with regular computing right now, you have your personal computer, but it's the data center where you get all your power here. So I think it's going to be more, data center kind of thing where there's maybe big data centers of quantum computers running the problems, and then you do them remotely. But I'm going to say from right now, quantum computers look kind of complex and expensive. So I'm not thinking that far out. But of course, that's what computers were like in the 50s and 60s. So, we'll have to see what happens. I'm saying I'm mostly focused on getting it to work, bringing the cost down, making it reliable, just to get the prototypes working properly.
So I'm gonna end it with one question. You've been at this for decades,
Right.
and there's so many brilliant people in this room and so many amazing companies in this exhibit hall. What's one piece of motivation you can give them that you've stayed motivated throughout all these decades to continue to do this work?
Yeah, so I started when things were very rudimentary and you could barely, see a signal. But the steady march of the field has been amazing over 40 years. And the amount of very clever ideas that come about, the ideas that, kind of surprised me over and over again. So although we might not, see exactly what we have ideas of where we want to go. We may not see everything or appreciate everything, but I have a lot of confidence that people will be able to figure out the problems and just get there. And seeing this over 40 years, it's amazing where we are right now. So,
Thank you so much for your contribution.
thank you.
Thank you. Bye-bye.